This is the second part of the 112 course, and we will start biochemistry in this chapter. So, by definition, biochemistry is the study of compounds and the processes that are associated with the living organisms. The first topic is going to be carbohydrates in this chapter. So, carbohydrates, or as we call it, carb, what are these? These are sugar molecules, and together with proteins and fats, carbohydrates, these are one of the three main nutrients found in foods and in the drinks that we consume. Your body, normally what it does, so that is the body, once you consume carbohydrates, your body breaks down carbohydrates into glucose. Glucose, we call it a blood sugar. This is the main source of energy for your body's cells, tissues, and organs. Carbohydrates, they are found in both healthy and unhealthy food. For example, they are found in bread, in beans, in milk, potatoes, popcorn, for example, cookies, pasta, drinks, fruits. So they are found in variety of food that we consume daily. They also come in different forms, and we're going to talk about their forms in this chapter. Now, the most common and abundant form, these are sugars, fibers, and the starches. So if you look at a simple carbohydrate molecule, it looks like this. It's made up of a carbon chain. The number of carbons in the chain vary from one carbohydrate to the other, and we will talk about this. But notice that carbohydrate molecules does have a lot of functional groups in it. So you have the hydroxy functional group, you have the aldehyde functional group, you also have the ketone functional group. This is why for carbohydrates we call those biomolecules. These are biomacromolecules, and these are big molecules, and they are made up of polyhydroxy aldehydes or ketones, because they do have functional groups in there. They do have an aldehyde or a ketone functional group, so this is why they are known to be a polyfunctional compounds in here. This is a simple sugar. Its name is ribose here, and ribose have, I'm going to highlight those functional groups. It does have 1, 2, 3, and 4 hydroxy functional groups, and it does have an aldehyde functional group as well. Carbohydrate stereochemistry involves the study of stereoisomers. So what are stereoisomers? Stereoisomers are a type of isomers. So far, we explained isomers to be compounds that have the same molecular formula. And from those isomers, we talked about constitutional isomers, which is the same thing, you guys, as structural isomers, if you remember. So that is the same thing as structural isomers. Structural isomers and constitutional isomers, these are the same. So for example, if we have, let's say C2H6O, okay? If I give you this formula and ask you, okay, go ahead and draw all the compounds that have this molecular formula. This means I am asking you to draw compounds that share this molecular formula but have different connectivity of atoms. And this is the definition for structural isomers. So structural isomers, there are compounds that share the same molecular formula, but they have different connectivity of atoms. This means that every time I'm going to name the compound, it's going to be a completely different name. For example, over here, I can draw two structures that have the same molecular formula as 2 carbons, 6 hydrogens, and an oxygen. One can be a simple alcohol, and the other one is going to be an ether. So when I want to name those, they're going to be completely different names. This one is going to be ethanol, and this one is going to be a diethyl ether. But these, they share the same molecular formula in there. So we call those structural isomers or constitutional isomers. These are types of isomers. They are completely different than stereoisomers. So what are stereoisomers? Stereoisomers, they still have the same molecular formula, but they have the same connectivity. So they have the same molecular formula. Let's go ahead and write it down. So stereoisomers, they have the same molecular formula. They do have the same connectivity of atoms. Okay, this is why they part from structural isomers. So here, stereoisomers, they have the same connectivity, unlike structural isomers that have different connectivity. The only difference with the stereoisomers is the rotation in space around the chiral carbon. So they have the different rotation in space around the chiral carbon. So as the name says for the stereoisomers, the stereo means rotation. So the only difference here that I have is the rotation around the chiral carbon, which we call it also a chiral center. So what is a chiral center? A chiral center is a center. It's not necessarily a carbon. Here I'm calling it a chiral carbon, but it can be a chiral nitrogen, a chiral oxygen. So it is actually a center that is connected to 4 different groups. The groups have to be different. They cannot be the same. And because they are 4 groups, that is going to force that center in there to have an sp3 hybridization. You need 4 orbitals in there, so it's going to be an sp3 hybridization. So by definition, a chiral center or a chiral, here in this case it's a carbon, so I'm going to call it a chiral center, okay, should have 4 different groups around it. So it should have 4 different groups around it. Now in this chapter we are limited to a chiral carbon. That's chiral carbon center in there. But the chiral center is not limited to a carbon. It's limited. It can be any atom that is an sp3 hybridization, and it has 4 different groups around it. So let's have an example over here. So if I give you this skeletal form and I ask you, how many chiral centers does this molecule have? Now I know that each one of these carbons in there is an sp3 hybridization, right? So what you need to do now, you need to look for the carbon that has 4 different groups around it. So if I'm looking at this carbon over here, I do have 3 hydrogens that are the same. So no, this is not a chiral center. Same thing here. As long as you have groups that are the same on that same carbon, then you won't have a chiral center. So no chiral center in these 2 carbons there. Now coming to this carbon over here, this carbon does have 4 different groups around it. Let's go ahead and label those groups so that you can go ahead and see them. So this is carbon number 2, 3, 4, and 5. So if I want to go ahead and draw carbon number 2 in there, what is it connected to? So carbon number 2 is connected to fluorine. It is connected to a CH3, okay? That is going to be the CH3 here. It's connected to a chlorine. And it is connected to carbon 3 that is a CH2 in there, and whatever group that is connected to CH2, because that one is carbon number 3, okay? You can easily see that all of those are different. The CH2 is different than the CH3. So you have 4 different groups in there This is why we are going to label carbon number 2 to be a chiral center. Okay, so that is going to be a chiral center. And to label the chiral center, we're going to use a small asterisk in there indicating that this is a chiral center. So that is going to be a chiral carbon, or you can go ahead and call it a chiral center. Okay. The CH3 here does have 3 hydrogens, so it is not a chiral center. So this one is the only chiral center that I have here. This is the chiral center. So my answer is going to be 1 chiral center. So here I have 1 chiral center. Okay, let's have another example in there. Again, a chiral center needs to be an sp3 hybridization. For us, you guys, we're going to limit our explanation to the sp3 hybridized carbon, meaning that the carbon needs to have 4 groups around it, and the 4 groups, they have to be different. Let's go ahead and look at those carbons in there for every single carbon. Now I know that all of these carbons on the benzene, all of them, they are sp2 hybridization. So I'm just going to group all of those in there and say that all of those, these are sp2 hybridization carbons in there. So you don't have 4 different groups. No 4 different groups. Each one of those, they do have 3 groups around them. So each one of these carbons is not considered to be a chiral center. And then you have the CH2 here. This is not a chiral center. This carbon over here, yeah, it is a chiral center. So let's go ahead and draw or magnify this carbon in there. So this carbon is connected to what? It's connected to a hydrogen. It is connected to an ethyl group. You can see that ethyl group, which is the CH2CH3, and a methyl group, and this whole thing there. So let's draw it. Let's use this color in here. So you have CH2, CH3, you can draw it anywhere you want. It really doesn't matter. So you have your CH3 in there, and then that is connected to a CH2, and I don't care what the CH2 is connected to there, and that is considered to be a chiral center because you can easily see all of these are different. Now, it will really help if you go ahead and you put what is next to the CH2 just to differentiate between this CH2 here and this CH2 in there. So you go with the 2 CH2s, these are ties. But whatever is connected to the CH2 is a CH3, whatever is connected to this one is a benzene. So definitely this whole group is different than this one. So this is why I come into a conclusion that the carbon, the center here, is connected to 4 different groups, okay? And I would call this again a chiral center. So this one is considered to be a chiral carbon, and it is a chiral center, meaning that it has 4 different groups around it. So this structure has only 1 chiral center. Okay, again, why 1 chiral center? Because again, over here I have no chiral center. Here I have no chiral center. So the only center that has 4 different groups is this carbon over here. You should be able to visualize it, guys. So if I have this structure in here, then I know this is a CH3, not a chiral center. Each one of these carbons is an sp3 hybridization. So don't let the hybridization confuse you. It's the different groups around the carbon that we are looking for. Okay, and if you have a double bond, then you have to take it out of the picture immediately because that is an sp2 hybridization, not an sp3. So these 2 CH3s are non chiral center. Coming over here, this carbon has what? It doesn't have 4 different groups. It has a hydrogen over here, you see that, and it does have the 2 CH3s that are the same. So this carbon in here is not a chiral center. This one is not a chiral center. But this carbon over here is a chiral center. Let's put a small asterisk around this carbon. It is a chiral center. So if I want to go ahead and magnify this, then this carbon, okay, is connected to what? It's connected to a CH3. It's connected to a hydrogen because here I do have a hydrogen. And then on this side, it is connected to a CH2 that is connected to a CH2, whatever that group is. And on the other side, it's connected to a CH2 that is connected to a CH. See the difference in there? It's connected to a CH and whatever that group that is connected to the CH. So this is why I keep writing down the connectivity until I reach a group that is different than the other. So I know that these two CH2s are the same, but this CH2 is connected to a CH, this CH2 is connected to a CH2, so I know that they are different groups in there. So that is a chiral center. Put an asterisk around the chiral center. And then what I have here, these two are CH2s, not a chiral center, but this one is a chiral center. So just put a small asterisk in there indicating that it is a chiral center. Let's go ahead and magnify this one. And this carbon is connected to what? It's connected to a CH3. It's connected to on this side over here. It's connected to a CH2, CH3. And I intend to write the CH3 because I know that there are two types of CH2s in here. So I want to differentiate between them. On the other side, I have a CH2 that is connected to a CH2. I don't have to write what is next to it in there. Okay, so it's this one. And then on that carbon, of course, I do have what? I do have a hydrogen. So go ahead and write the hydrogen. And that is another chiral center in there. And that chiral center has 4 different groups around it. So here I do have for that molecule 2 chiral centers. Guys, to represent the chiral centers, we simply represent them by an asterisk on where the chiral center is. There are different ways in order to represent a chiral center or a chiral molecule in there. The first way is simply to draw it in a 3D structure. So let's say if I give you this structure here and ask you, find the chiral center and draw it in a 3D. So the first thing that you would need to do is locate the chiral center, put an asterisk around it in there. We know that that chiral center is an sp3 hybridization, right? And an sp3 hybridization has a geometry of a tetrahedral. And a tetrahedral carbon, as you already know, is a carbon that has 2 bonds in plane, 1 bond in front, and the other one is behind. Guys, you can lay down these groups anywhere you want around the carbon. It really doesn't matter because this is a chiral center and there is a rotation around that chiral center. So if you put the acid here in front or you put it in plane, it doesn't matter. Remember that those lines in there, these are indication that the groups are in plane versus the wedge, which is in front, versus the dash, which is behind. We prefer to put the carbon chain in plane. So here the carbon chain is the CH3 and the acid. So we prefer, it's not a must, but we prefer to put the carbon chain in plane. This is it over here. You can put the acid here, the CH3 there. It doesn't matter because, again, think about it. You can rotate around this carbon. So it doesn't matter where the acid is. It doesn't matter where the CH3 is. The NH2 can be over here. the hydrogen can be at the back. And this is one way of drawing this molecule in a 3D. You can also draw it like this, as I said, because there is a rotation around that chiral center. So this chiral center, there is a rotation around it. So again, it doesn't matter. I can, for example, put the CH3 over here. I can put the acid in there. I can put the hydrogen in front. I can put the NH2 at the back. So it really doesn't matter in there. Are these two the same? Well, connectivity-wise, they are the same. But the rotation around this carbon is different, which makes those two to be stereoisomers. Okay? So this is one way of drawing a structure with a chiral center. Another way, which we're going to use in carbohydrate representation, is the Fisher projection. So when do you use Fisher projection? Fisher projection is a useful way to draw more than one chiral center. Of course, you can draw one chiral center in Fisher, but you can normally use it if you have more than one chiral center. It's easier than drawing the 3D representation. So what is Fisher? Fisher is actually two lines. It's kind of like a cross in there. And those two lines, you do have a vertical line, you have a horizontal line. Now that vertical line means that the groups on it are behind. The horizontal line means that the groups on it are in front, okay? And when these two meet, they meet in a carbon. And that carbon in there normally is a chiral center. It depends on the groups around it. Sometimes it is, sometimes it is not, but it depends on the group around it. The groups around it, they have to be 4 different groups. Like for example, in this example over here, I want to change this into a Fisher projection. So all what you need to do is simply draw the cross in there. They meet in a carbon. So that is the carbon where they meet at. This is the chiral center. So I'm just going to go ahead and label it as the chiral center. And then you can distribute the groups anywhere you want, guys. So what I see over here is the acid and the CH3. I'm going to put the acid up there, and I'm going to put the CH3. And then I do have my NH2 here, and I do have my hydrogen in there. So the NH2 and the hydrogen, both of those, they lie in front, and the acid and the CH3, both of those, they lie behind. That is the Fisher projection in there. Normally what we do is that whenever you have a carbon chain, we care about the carbon chain being on the vertical line whenever we want to represent it in the Fisher projection. See, whenever you are representing a structure in 3D, we care about the carbon chain to be in the plane. And in Fisher projection, we care about the carbon chain being on the vertical line. So here I know, by the look of it, I know that I have a structure that is made up of 1, 2, and 3 carbons. This is how I count the carbons. Now, let's say if I have more than one chiral center, then I'm going to go ahead and draw my horizontal lines, my vertical lines, and where the horizontal and the vertical lines meet, that is going to be my chiral center in this case. Okay, so let's have this example over here. I ask you go ahead and change this into a Fisher projection. So the first thing that you would need to do is locate your chiral centers. And here I do have 1, 2 chiral centers because these are the only carbons with 4 different groups in there. I'm going to number my structure in there. This is 1, 2, 3, 4, and 5. I started numbering it from here because this side gives the OH the lowest number. so that we are all on the same page. Always, whenever you want a number as if you are naming, although you are not naming. And then I know that it is two chiral centers in there, so I would need my horizontal line and my vertical lines to meet. This is the first chiral center, and that is going to be the second chiral center in there. Put like an asterisk in there, put an asterisk in there, and I'm going to start by numbering from the vertical line. Remember what I said, that always the carbon chain is better if it is on the vertical line. So over here, I do have carbons 2 and carbon 3, right? Because both of those are chiral centers. So on 2, what do I have? On carbon number 2, I do have a CH3. Keep it on the horizontal, on the vertical line. So the CH3 is all the way up there. And then on carbon number 2, I have a hydrogen and an OH. Guys, it doesn't matter where to put the hydrogen and the OH. So I can put the hydrogen here, the OH there, or I can put the hydrogen here and the OH there. It really doesn't matter. So I'm just going to choose the hydrogen to be on the left, the OH to be on the right, but you can reverse those. It's not a big deal in there. And then on the third carbon, what do I have? This is a chiral center. It is connected to a CH2, CH3. Keep it on the vertical line. So this is a CH2, that is a CH3 there. And then it is connected to a hydrogen and an OH. So again, I'm just going to go ahead and put a hydrogen here and an OH there. You can reverse that and put a hydrogen and put an OH here and the hydrogen there. It doesn't matter. If you do, then you're going to end up getting the different stereoisomers there. So it really doesn't matter where to put your hydrogens and OHs, but make sure that the carbon chain is along the vertical line. Locate every chiral center, see what it is connected to, and go ahead and draw the groups. Okay, let's have another example. And see, you can easily see here how the Fisher projection is kind of like an easy way to represent a structure with more than one chiral center. So if I have like 3 chiral centers, as in this example over here, and I ask you, okay, go ahead and draw the Fisher projection, then just make sure to draw your vertical and horizontal lines and let them meet at 3 points there, so that you can represent your Fisher projection for the structure. So this is 1, this is 2, and that is a 3. And I'm going to do the same thing. I'm going to locate my chiral center. So this is a chiral center, this is a chiral center, and that is a chiral center. Put an asterisk above each one of those. I should have started with the aldehyde, right? Because we know that the aldehyde is higher priority than the OH. So this is a 3, this is 4, and that is 5 in there. Always when you draw your structure, start carbon number 1 from the top of the vertical line. And we agreed that the long carbon chain is going to be on the vertical line. So that is going to be carbon 1. I have carbon 2, carbon 3, and carbon 4. All of those are chiral. And then I would have carbon 6 in there, or carbon 5, I'm sorry. Carbon 5 is a CH3. Carbon 1 is a CHO, which is an aldehyde. There, and then you go ahead and you put your hydrogens and OHs anywhere you want. So I'm just going to go ahead and put the hydrogen, the OH here. That is on carbon number 2. We're done from that. For carbon number 3, it's again connected to a hydrogen and an OH. So we're going to put that. For carbon number 4, we do have a hydrogen, we do have an OH. Again, I can switch the hydrogens and the OHs, put the OH over here, put the hydrogen there. It really doesn't matter. This is one representation, one Fisher representation of this structure in there.